Okay, so for those of you who skipped the last video, the idea is that we want to learn system design through games, and how we're going to do that is we're going to take games and break them down into systems, right? Break them down into constraints, into variables, and we'll see how these variables interact with each other and how they affect the game system. Why I think this helps later when you're actually doing system design in the software domain is because even there are constraints, and it kind of teaches you or sort of trains your mind to think of those constraints first, right? Because it gets used to thinking in a certain direction. So we're going to take the example of chess, right? So I'm going to assume that you know the basics of chess. After that, let's try to sort of build a system which represents chess, right? So when you think about chess, uh, you have a certain goal, right? So there's a goal which could be winning, could be draw, it could be losing, right? The depending on what's going on, it could be either one of these states, right? And then you would have your the state of the board, right? And what we can do is we can sort of define some variables which which can quantify the state of this board, right? And that is going to help us to sort of make a mental model of what's going on. And then basically what will happen is based on how the game is going or based on certain constraints, we can sort of come up with a strategy, right? Based on those variables, right? So for example, let's see. So chess has some pieces, right? So I'm gonna assume that you already know the rules of chess. If you don't know, you should pause the video and maybe go and look it up before continuing. So each side, so this is side A and side B. Let's assume we are side A and the opponent is side B, right? So we want to sort of quantify the position and kind of try to define whether we are winning or losing, and maybe define a function which is similar to like an optimization function, and that function would kind of dictate where our goal would be to kind of modify that function. So the state of the game, we're going to try to represent it as some function, right? So in order to do that, let's kind of define a couple of variables, right? So we know that there are some pieces, right? We have a pawn, we have a bishop, we have a knight, right? These pieces exist, right? The first thing what we're going to do is we're going to assign some value to these pieces. So for example, a pawn would have a value of 1, right? A bishop would have a bishop or a knight actually would have a value of 2. A rook can have a value of 3, and queen can have a value of 7. I forgot. I think there's some standard value for the queen, maybe 5 or 7. I think it's 7. And then I think that's about it, right? So let's kind of think about what opposition matters, right? Like one way I like to think about it is if you take extremes, it kind of makes it easy to sort of understand how this variables would sort of affect your game state, right? So, like if you think of an extreme where you have one pawn and like one pawn and a king, and the opponent has like four queens, right? For sure you are losing, right? For sure the opponent has a better position. So the number of the sort of net value of your pieces, that's one thing that does matter. So the first variable I'm going to define is the net value of the pieces you have, right? And let's just represent it as this summation symbol. So for example, if you have two pawns and a bishop, you would have a net value of uh, four, basically, because two pawns and a bishop, right? Now, the opponent would also have like a similar net value, right? The opponent would also have like a summation based on what kind of pieces they have. Now, let's think about it. Is this enough? Is having more pieces or having more pieces than the opponent, is it enough? Like if there's a knight uh, which is there, does it really matter where the knight is, or it just matters that the knight exists? So I think the position also matters, right? So for example, you could have a bishop which is sort of trapped, like maybe you have like two pawns, a pawn, pawn, and a pawn, two pawns like this, and then this is the end of the board, right? And then you have sort of a bishop over here. So the bishop is kind of trapped, right? Because of the two pawns, it will get trapped. So the position, what I'm trying to say is that the position of the pieces would also matter. The individual position of the pieces will matter. The sort of cumulative position would also matter. So let's kind of define P as our next variable. So this is variable number one. And then for variable number two, we say, okay, let's call it P. So P is the net position of how your pieces interact with each other, right? So now you have the summation of this and P, right? So for a particular game state, I think these two are, I think they work, right? These two can work. We can say that, okay, it depends on this and it depends on P, right? And we define it for this is A, and then opponent also has something similar, right? Let's put it over here as B and PB, which is the position of the opponent's pieces and the summation of the piece values. So this is essentially sort of like the cost function that we try to optimize in chess, right? So for example, what we want, so we know that the summation of value cannot actually go up, right? It can either stay the same or it can go down because you can't add, actually it can go up in edge conditions where you promote a pawn, right? So, but what we want to do is we want to sort of increase this top part and we want to try to decrease this bottom part, right? And if we do that, if you're successful in doing that, we're going to win that game. If provided our goal is to win, right? Sometimes, normally our goal would be to win, but like there would be situations for draw and lose also. Like for example, for draw, I can think that okay, maybe it's if it's a team, like a team of five versus five, and there's some sort of a format, and a draw still gets you to the next stage. It's possible that you want to draw. Maybe some position for lose as well. Like taking it as an extreme, you could think that you're cheating, you're cheating, and you don't want the moderators to sort of find out that you're cheating. So some of the games you would kind of your goal would be to lose, so as to not draw suspicion towards yourself, right? So based on your goal, this state, let's just call it the SG, right? Global state is what is sort of like the cost function you want to either increase or decrease, right? And each move you make can kind of transition this SG1 into SG2 into SG3, right? So you start with a certain state and then you make a move, and that move is going to affect either the position or the summation of the value or for your pieces or for the opponent's pieces. And based on that, the state is kind of going to change, right? So are there any other, so in the game state, these are the variables. But when you think about, the person actually making the move, that person would also have some variables, right? So for example, um, the let's call it let's say let's take SK as the skill, right? The skill. What is skill over here? The skill is the skill to judge this equation essentially. So the skill to understand whether a particular position is good or bad. So for example, if you move your bishop from a certain place to another place, does that increase P or not? Or if the opponent moves one of their pieces from one place to another place, does that reduce their P or not? So that's the skill. right? And skill to judge the state, essentially, right? So you need the skill, and the skill to judge is everything, right? Because that's your move. And when you make a move based on the skill, you're going to be able to sort of modify this cost function, right? And the skill would depend on one, your sort of your actual skill. Like for example, your like Magnus Carlsen would have a better, like easier time to judge the pieces, right? Judge the position than you. So that's the skill. And it would depend on some factors also, right? So for example, it could depend on, I think it would depend on time, right? The time you have to essentially, judge the position, right? So it depends on the skill matters in making a decision, the time matters in taking a decision, right? These two things matter. So for example, you can kind of think of a scenario that where let's see, is there anything else? The state of the individual can also be maybe be considered in skill, like which state he is in, whether he's, it's tired or not. Maybe it's all part of skill. Time definitely matters. Is there any other variable that we can think of that could come up over here? Let me think. So, the time you have to make a decision would matter. The skill would matter. Let's just take these two for now. So, for example, suppose your goal is to win, right? And you're playing a game, and suddenly you sort of, oh, okay, I can think of another one. So, the complexity of the position would also matter, right? The complexity of the position. So, when you talk about a move to change states, it depends on three things. It depends on the skill. Let's just call this skill, which is one. You have time, right? And the complexity of the position. What I mean by complexity is that if there are like four pieces on the board, it might be easier to judge the position versus if there are like all the pieces are there and it's very interrelated, those pieces are interacting with each other, then the position could be really complicated. So that could also play a role. Like for a more complicated position, maybe it's harder for someone to judge this equation, right? Let me clear this up and just write it in maybe a little bit of a simpler manner, right? So we have skill, time, and complexity, and so our cost function becomes your summation A and your position of A, right? Just to recap, this is the sum of the values of your pieces and piece the position of those pieces. And then you have the opponent's position and values. And this is basically your global state. And the ability to kind of each move you make can kind of transition this SG1 into SG2, right? And that transition, whatever you're going to do, would depend on one, the skill of the individual to judge the position. Two, it would depend on the time, right? So if Magnus Carlsen would have like half a second to judge a position, he probably won't be able to judge it as good as he would if he had, say, 5 minutes to judge it, right? And the third one is the complexity. So based on how complex the position actually is, your ability to judge would kind of change, right? So now, think about this, right? So now we have this system. So we've defined this system, and of course, usually these systems are made up of even more complicated systems. For example, this P can maybe be broken down into another system, right? But for now, let's keep it as this. And what I'm trying to say over here is that suppose your objective is to win, right? And imagine you're playing a game of chess. Your objective is to win, and you end up losing a piece for free, right? You lost a piece, so suddenly your sigma A is smaller than sigma B. So that is the constraint which happened in the game. Now, what would be your strategy? What could be your strategy to win this game? Suppose you lost a piece, right? So sigma A is smaller than sigma B, right? Or maybe just to take a simple case where the positions are equal. So you start with the handicap. right? You're playing against a person and you're starting with a handicap. You don't have a bishop, right? So sigma A is smaller than sigma B, and your PA is basically equivalent to PB, right? It's quite similar. There's not much change in that. So now if you're playing, what should your strategy be to win, right? This function you need to maximize, right? And what can you affect in this system? Let's think about it like that. What can you affect? Can you affect the skill of the opponent, right? In most situations, probably not, right? The skill is something which is innate to the human, so I don't think you can affect that unless you have a way to get them to maybe drink alcohol, intoxicate them, or something like that. That's a different different thing altogether. But usually, maybe not the best strategy to kind of target this one. Time, can you affect the time? Suppose you're playing a timed game. So yeah, you can affect the time, right? If you play faster, right? If you play faster, then that leaves them with less time. And what that would mean is that it would hamper their ability to sort of judge what PAPB is and judge the state transition. So one strategy could be that you want to put them under time pressure. That could be a strategy. One strategy could be complexity. If you increase the complexity, right, there's a chance that they make more mistakes because you've increased the complexity, so it's harder for them to judge the state transitions, right? But this would also, by the way, mean that it would be harder for you also to judge the state transitions because the game is more complicated. The time is a good measure. So if you think about each, suppose you're playing as A in this, right? So for A, what could your strategy be? What would you want to do? You would want to try not to reduce complexity, right? Because if it's not complicated at all, like there are very few moving parts, then you're probably going to lose, right? Because you're down on this and there's the complexity is very low, then you're going to lose, right? So you wouldn't want to simplify the situation, is what I'm trying to say, right? You would try to keep the pieces on the board, not trade pieces. Like if you have an option to trade a knight for a knight, you wouldn't want to do that because that would reduce complexity, right? And it would be in your interest to increase complexity. For the opponent, it would be different, right? If you're playing as B, what you would want is to just to trade off the pieces, right? Because that would decrease the complexity and help you kind of win. And the other factor is time. You have to play fast, right? So if you can play fast and avoid simplifying the game, I think that would be an okay strategy to go with, right? And for the opponent, it would be, different, not being put into time pressure, right? So not taking too much time on the moves and trying to reduce the complexity. That would be their strategy. So this is what I'm talking about, right? The idea is to kind of break it down into systems and then look at the constraints and then think about how they change, right? Based on a certain situation, think about what kind of a strategy you could take and how they would change. Like for example, if I say, okay, you're not playing against a human anymore, right? You're playing against a robot, right? You're playing against AI. How would these change, right? Same situation, right? This is where the summation of pieces is you're starting with a handicap, the position is equal, and the sum of the position of A is smaller than the sum of position B. But you're playing against the robot and you're playing as person A, right? Now, like, would the same strategy work, right? Putting the AI into time pressure, does it make sense? No, right? Because AI would kind of just play at the skill level, and for the AI, because it's computing the next move, the time and complexity is actually irrelevant. It's just going to play the at whatever level it's trained to play at, right? It's not going to take a lot of time for the moves. It's not going to take a lot of like the if you increase the complexity, it might or might not affect it. But like I would argue that this would affect a human a lot more than it affects AI, right? So I would say that within these constraints, it would be easier to win a game against a similarly skilled opponent, whereas suppose your SKA is actually similar to SKB, similarly skilled opponent, if you're playing against a human, because if you're playing against an AI, the strategy that you can go for is really hard, right? You're gonna have to basically forcibly play better than B. You're gonna have to make sure that you make better moves than B. But if you're playing against a human, it's not really necessary to play better than B. You could win on time, you could win on complexity, right? There are other factors which you can leverage, right? So why I feel thinking in this sort of a manner affects, your thinking ability and the way you think about systems is because even in system design, when you sort of get a question, you have to think in terms of these variables, right? That's all there is. You have to think in terms of these variables, and you have to think of the constraints there are. And based on that, the system that you're going to design is changed. Like I know over here we made the system first, and then we kind of decided, okay, how do these constraints affect the system, right? But once you start, so in chess, basically the game state doesn't change a lot. Like for example, if and if chess, if the pieces also changed, if there are like random constraints which kept happening, you're gonna have to probably keep iterating on this. But that's the idea. So for example, if you go to, if you let me clear this out, right? So suppose you go for a system design interview and they say, why don't you design YouTube, right? Instead of designing YouTube, you have to think, okay, what are the variables which actually affect my design? So you have a certain system which you're expected to architect, which is probably made up of subsystems, right? Internally. So you're gonna have to think like that. Like my main system, what variables actually affect this system, right? For example, does the number of requests, does this affect the system? Do you think this would affect it? Like suppose you have to make a system for maybe 10, like only for like uh like if you had to make this system only for one college, right? Versus if you want to make it global, do you think that would affect the system, right? Uh, then you could think about latency, right? Does it matter? Would it affect the system in any way? Right? Is there an expectation on latency? Then you can think about the storage, right? How much uploads are we actually expecting? What is the quality of those uploads in terms of memory? Would that affect the system? Like for example, if you say that okay, we're gonna design for global and we want like low latency, right? Low latency for now, when you say low latency, it could be low latency, okay, for consumers, right? Or for maybe the producers who are actually uploading the videos versus, people who are consuming the videos. Maybe for the people who are uploading, uh, higher latency would be okay. Maybe they don't doesn't need to be really fast, right? But that's a business call to make, right? In storage, you can think about okay, how much storage do we need? Do we need to retain that storage? Right? So for example, if I change these constraints, you could come up with like it's possible that your system becomes very different, right? Like for example, if I say that you want to make a blog site, right? You want to make a blog site, right? And you just want to serve your college, right? So your college has like maybe you have like 2,000 people in college. That's it. And like how many of these are actually going to come and read your blog, right? So maybe a small percentage, right? So concurrent, if you think about concurrent requests that you're going to have to service, maybe it's really less, right? Maybe 10, 20 concurrent requests you need to serve. You actually wouldn't need all that architecture, right? You could just have one server which sort of provides HTML, CSS, JavaScript, whatever files to the UI. You don't need a database. You can just save it on the file system, right? If you think about storage and it's your personal blog site, suppose you're even uploading every day, how much storage would it even take, right? Is 10 GB of storage enough? Then you could just host it in the file system without a database, right? On the other hand, if you say, okay, I want to make a blog site for global, right? I want to make a blog site for a business, basically. So there's a business who wants to make a blog site, and they want to serve their customers globally, and they have a team of content creators, right? And the upload cadence and the amount of they're going to upload is a lot. Then you won't be able to do that. You're going to have to decide on a different way to go about it. So what I'm trying to say is, like, if you think in terms of the constraints which are going to affect your system, it's going to be it becomes easier to sort of understand what, like, how to design that system, right? So for example, you said, and what happens is, because of these constraints, you could actually find high leverage situations which you can uh, sort of use in your design. Like, for example, suppose you have to make a stock market trading, right? Stock market trading, uh, like something like a national stock exchange portal, right? Where people can come and they can trade, right? You can actually find constraints which are very unique to that business as well, right? So stock market is open what, from 9:30 to 3:30, something like that, right? So you know that this is where all the traffic is going to go. If at night at 2 a.m. to 6 a.m., even if your system is completely down at this point, it doesn't matter, right? It's not going to affect the users. So you can actually maybe do, like, use this, that the fact that the system doesn't need to be available during this time. You can use this fact to maybe perform some data migration activities, or to sync data across different nodes of a database. What I'm trying to say is that if you start thinking in terms of constraints and things in terms of the inputs which are going to affect your system, you can kind of land up with uh, certain situations which you can take advantage of, right? So I think I'm gonna stop this video till here. Maybe in the next video we can actually go and try to apply the system in an actual chess match, and we can see how it should change, right? We're gonna do it in the next video. But I hope you understand the point I'm trying to make. If you feel like if you have any questions, or if you feel like there's something that you wanted me to cover, and but like I didn't talk about it, or you're not sure how this would finally relate to system design, please feel free to comment on the video. I'll definitely reply. Also, just like a quick note on what I feel we can do is that, instead of just like keep just staying in the game domain, I don't intend to do that. Initially, I'm just kind of I'm going to teach how to break stuff down into systems, how to think in terms of constraints using like a game domain. But ultimately, once we're like good at that and we've done it for a couple of games and maybe played a bit of games, we're going to switch. We're going to switch back to the system design domain, right? And we're going to actually dive into the actual system design questions, because all this is completely useless if you're not able to actually apply it to system design. So yeah, it feels good to see, okay, maybe this might work, but it needs to actually work, right? We need to actually make those system designs. If you don't do that, then all this becomes sort of like useless. So we're gonna try to learn this skill and practice this skill for some time, maybe with a couple of different games. And then we are going to switch into an actual system design question and use the exactly the same things we were doing over here. Maybe we'll even make a framework, right? I think it would make sense to make some sort of a framework that, okay, first we need to think about the inputs, right, and the assumptions that we're taking. Next, we think about constraints, and then we could have a certain framework which we can follow, which we can apply to this as well, and then we can apply to the system design questions as well. But just to call it out, we're not going to stay in the game domain forever, right? We're just going to learn the skill and then we're going to switch to see how the skill actually transfers into an actual system design interview, right? So I think that's it for this video. So let's maybe I'll catch you in the next one.